The conference dinner. So first talk today is Hoon Lee.
Hoon Lee, yeah.
I will be speaking on branes and trace relations. I think I have 25.
So if it's okay, I'll stand over here because I'd like to read my slides. And so thanks a lot to the organizers for the invitation to speak. I'll be speaking about branes and trace relations. So, so my talk will be about gauge and string theories, but it'll be in a regime, namely finite n regime, where it's a bit scary for integrability. But so the idea that a large n gauge theory reorganizes into a string theory has a long and fruitful history, as reviewed also in earlier talks, dating back from Tuft and coming to full bloom in ADS-CFT correspondence. And so perhaps the most basic qualitative statement is that a state labeled by gauge invariant words in a large n gauge theory is dual to a state consisting of closed rings propagating in a bulk spacetime. And just using this statement, a whole lot about the large n thermodynamic properties of string theory on ADS backgrounds can be inferred from this, especially at weak Tuft coupling. The reason is that at lambda equals to 0, the partition function of a UN gauge theory counting gauge invariant states on S1 cross S3 reduces to a unitary integral over a holonomy matrix U. So the large n saddles of this matrix integral correspond to the thermodynamic phases of the bulk in the stringy regime. And if you consider F, which is that of a supercontrol index in, say, n equals to 4 superrang mils, these saddles can be interpreted as a sum over BPS families of Euclidean black holes. So the main question that I'll be discussing today is what would happen to the statement that I mentioned earlier when n takes a finite integer value. So at finite n, there's an apparent tension regarding the spectrum of states of the bulk and the boundary theories. So in the boundary gauge theory, states formed by exciting the vacuum with single trace operators are orthogonal at large n, but become constrained by trace relations when n is finite. So for example, at n equals to 2, a single 2x2 matrix valued scalar satisfies the following infinite tower of trace identities. And so on, where every trace of x to power greater than 2 can be decomposed in terms of sums of products of lower traces. Okay, so therefore the total number of states at fixed values of conserved charges and lambda would decrease as n is decreased. And this is a boundary expectation. But in the bulk, non-perturbative states, such as black holes and D-branes, get lighter at finite G-string. So these objects, which are present in addition to the perturbative string states, would naively result in more states at finite G-string compared to those at small G-string. Okay. So how does one reconcile these differing expectations? To avoid a paradox, it's typically posited that non-perturbative objects in string theory represent highly redundant descriptions of the same set of quantum states. And so much so that the non-perturbative effects actually need to cut down the total number of states at finite n. Okay. So this phenomenon, or this expectation, goes by the name of the string exclusion principle. But it's more of a name for a phenomenon that we don't quite understand yet. The giant graviton expansion is a recently proposed formula which relates the BPS sectors of gauge theories and their string duals. And as I'll explain, this formula gives some clues as to how the string exclusion principle may be realized at the level of the bulk spectrum. So how do we understand this formula? Z sub n, the superconformal index of UN n equals to 4 superrang mils, reorganizes into a sum over BPS indices computed in ADS 5 times S5 labeled by K D3 giant graviton branes. Okay, and so giant graviton branes are branes which wrap S3 and S5 and are supported by a large angular momentum induced from the Riemann-Roman 4-form potential. So this Z infinity is the index of S5 KK modes, and this factor is the index of K wrapped D3s and quantum fluctuations. So pictorially, you can view this expansion in this manner. So this is an exact finite n expansion. So for the 16th BPS index, the n dependence organizes nicely into these alternating sums of contributions from branes, which has an independent definition. So to understand the properties, let's just stare at the formula in the simplest half BPS example. In the half BPS sector in n equals to 4 superrang mils, it's a purely bosonic sector consisting of these operators, or these states, modulo trace relations at finite n. And this gives you the left-hand side. So in the bulk side of the formula, the kth term on the right-hand side comes from k coincident wrapped D3 branes and half BPS excitations thereof. An important feature here, the key feature, is the alternating signs in the bulk side of the formula, which results in large cancellations in the bulk spectrum that you can't see from the boundary perspective. So BPS spectra in ADS 5 times S5 in the presence of K-wrapped D3 branes exhibit large cancellations to reproduce the finite n answer, which I think is how the stringy exclusion principle is realized in this setting. And I'll discuss the bulk and boundary computations. So in the remainder of this talk, I'll provide an explanation of the right-hand side, the bulk side of the half BPS expansion, both in terms of the bulk and the boundary. The result that we get turns out to be rather unexpected and seems to suggest clues for understanding aspects of the ADS-CFT dictionary at finite n. So to compute the contribution of a wrapped bulk D3 brane in the half BPS partition function, the half BPS index would also go in a very similar way with minor modifications, because the half BPS index also needs to be defined as a projection onto some charge sector via taking some limit of the fugacities. Okay. So to compute this in the bulk, I'll consider a thermal Euclidean ADS 5 times S5 with the background chemical potential for the relevant R charge. So the chemical potential is now built into the metric, where we have a thermal circle, and Q stands for, is a fugacity for the chemical potential mu. So I'll be considering a Euclidean D3 giant wrapped, so we're computing a thermal quantity. I'll be computing considering a Euclidean D3 giant wrapped on S1 and S1 cross S3 in ADS 5 times S5. And the Brane solution, it sits at the center of ADS5 and wraps a maximal S3 and S5. The on-shell contribution from this Brane is Q to the n. It's readily computed. And the one-loop Brane partition function, which we have to extract by taking this beta large limit, we need to project onto the BPS sector, is given by this. Namely, the actual only important term is this blue term for n equals to 0. This term arises from two unstable bosonic modes on the world volume, whose contours need to be rotated in the imaginary direction to be well defined. So the two factors of i's give an overall minus sign for Z1 loop. So there's an overall minus sign there. Okay, so what should be surprising here is that the overall minus sign in the contribution of a single wrapped D3 brane, which starts causing large cancellations in the giant graviton expansion, as we saw. This has a purely bosonic origin. So the state counting interpretation of the quantized open string modes on this brane resembles that of a ghost. It's a bulk effect that whose role is to remove states from the spectrum. So we should ask what these states are in the boundary gauge theory shortly. And the contribution of the K-wrap branes can be computed by imposing UK gauge invariance on the single particle spectrum from the one brane answer. And this reproduces the formula that I claimed earlier. Okay. Each summand of the formula that I claimed earlier. So what are the states, in quotes, in the boundary UN n equals to 4 superrang mils, whose spectrum yields the spectrum of KD3 giants in ADS 5 times S5? So these states, in quotes, cannot belong in the physical Hilbert space, H sub n of UN n equals to 4 superrang mils in the half BPS sector, right? So a hint comes from observing closely the terms in the expansion. The spectrum of a single wrap brane coincides with that of the spectrum of finite and trace relations that must be accounted for in the BPS sector. So namely, this term is it represents a tower of trace relations, which start of a single matrix, which start at R charge n+1, n+2, and forms an infinite tower. Okay, so let's impose the finite n constraints via, so in the gauge theory, we're treating the finite n constraints via a BRST procedure where we introduce auxiliary ghosts with dimension and R charge starting at n+1. In the boundary U infinity gauge theory, that compensate for the presence of trace relations that would be present in a UN theory. Okay, so we're simply changing variables here. The effect of introducing these anti-commuting ghosts along with a homological charge Q hat, the word homology is just convention rather than cohomology, which agrees with the math literature. So it acts on the anti-commuting ghosts in this matter, where these PNs represent the trace relations. Okay. So the effect of this procedure is to reduce the U infinity theory to a UN gauge theory. And these auxiliary ghosts are not just to clarify, they're not the BRST anti-ghosts. But their role is to simply supplement the U infinity theory with directions for systematically removing all but the UN degrees of freedom. So it's simple to compute the spectrum with ghost number k in the half BPS sector because this sector does not have ghosts for ghosts. Okay, so in general, you can, with multi-matrices, you can have ghosts for ghosts. The states with ghost number k are multi-ghost states built out of k chi's, and we can write a basis of k multi-ghost states in this matter, which has this spectrum, which we saw from the bulk computation of the BPS spectrum of k-wrapped D3 branes. And the signs -1 to the k must be included here because the ghost chi are implementing null relations. So by matching of the spectrum, our findings suggest that the BPS states of certain D3 branes in ADS 5 times S5 should actually be identified with certain auxiliary ghosts which implement the trace relations at finite n in n equals to 4 superrang mils. What does the identification between the half BPS states of bulk D branes and these auxiliary objects in a suitably rewritten boundary UN n equals to 4 superrang mils suggest about the bulk half BPS space of states? So we can organize the space of multi-ghost states with coefficients in the ring of polynomials of traces into a complex. This is actually a standard BRC resolution treatment of the constraints. Okay? So where where Vk is a space of multi-ghost states of ghost number k with coefficients in the ring R. And H infinity is the happy PS Hilbert space of n equals to 4 superrank mills at infinite n. And this Q is a differential which acts on operators via the graded Leibniz rule. So this complex has a non-vanishing homology only at ghost number 0. And since this image is the space of trace relations by design with coefficients in R, the homology at ghost number k equals to 0 you get back the Hilbert space that you want, okay? In the half BPS sector of UN n equals to 4 superrank mills at finite n. So as is usual, when the space of states is presented as a complex, you get the physical Hilbert space by looking at the cohomology of the differential. So let's observe that each Vk in the complex is a Fock space built from the multi-ghost generators. So namely, these are free modules over R. So this means that if we augment the complex with H sub n at the final step, the resulting exact sequence is a free resolution of the half BPS space of states at finite n. So roughly speaking, a free resolution is the procedure of replacing a highly constrained space, H sub n, with the sequence of unconstrained Fock spaces V sub k, whose generators represent the constraints on H sub n. But the novelty here is that these V's were identified with the space of quantum fluctuations of k Euclidean branes in the bulk. So the resolution gives a precise relationship, which can be generalized, but it discussed in the half BPS sector here, between the half BPS space of states H sub n of UN n equals to 4 superrank mills at finite n, and the complex identified as the half BPS space of states of ADS 5 times S5, found by summing the contributions of wrapped D-branes and their quantum fluctuations. Okay. And you get the physical space of states by taking the homology of Q hat. The resolution says that open strings on certain D-branes are encoded in the relations between the single trace generators that arise in the boundary theory at finite n. So it's simple to use this observation to recover the half BPS expansion simply by using the identity for exact sequences, that the alternating sum of the dimension of spaces in the complex vanishes. And we've just moved one factor to the left-hand side. So the close ring, the KK spectrum in the half BPS sector factored out from the perspective of the complex because Vk are free R modules and Z infinity is the half BPS partition function of H sub infinity. Okay, so in this talk, I've shown that the BPS spaces of states Vk of ADS 5 times S5 with K wrapped D3 branes at various K form a complex which furnishes a free resolution of the BPS Hilbert space of UN n equals to 4 superrank mills at finite n. This suggested that spaces that the states of certain bulk D-branes in ADS 5 are encoded in the finite n trace relations between the single trace operators and n equals to 4 superrank mills. And so the analysis of the Brane path integral in ADS 5 times S5 and the BRC resolution of the finite n constraints in n equals to 4 superrank mills is readily generalized beyond the half BPS sector. And this is what these references are where the Brane path integral were considered in the Schur sector of n equals to 4 superrank mills and type 2b on ADS 5 times S5. And this is a reference where a more general BRC resolution was explained. So these lessons can be used to understand aspects of the finite n BPS spectrum and the thermal / grand canonical correlators in holography. So it's a consequence of this previous formula that I showed. So it's a consequence of having having a free resolution, that such a formula actually holds for grand canonical correlators. So one can relate the grand canonical correlator in finite n equals to 4 superang mils, perhaps in the BPS sector, with an alternating sum of correlators computed in the bulk, in the background, in the 80s 5 times S5 in the presence of these bulk D-branes. So that's all I wanted to say. Thank you very much for your attention.
Thank you for your talk. Questions? Do we have more microphones?
So your master formula looked a bit like a trans series.
Yes,
Okay.
except it doesn't have the asymptotic series. It has the exponential terms, but it doesn't have the asymptotic series.
Yeah, but each term is a kind of instanton-like action, or
Yes.
maybe these D-branes, and
Yes.
then you had this perturbative. Okay.
Yes, yeah. So it is quite reminiscent of that, except that it seems to be missing the 1 over n asymptotic series that's present in the trans series.
Thank you. And another point. So you in n equals 4 super Young mills, you organize the observables in terms of these single traces. But could you organize in terms of determinants or something similar objects instead?
So determinants at finite n, recall that determinants can always be written in terms of the traces. So they're no longer, they're not orthogonal from the traces. However, there is a connection to the determinants. So the connection is that determinants is a generating function for the trace relations. So you can exponentiate and write the e to the log of the determinant, and if you exponentiate the determinant, this log of the determinant, it's you get a generating function for the trace relations for a single matrix. So that's the connection to determinants.
Thank you.
Yes, in the bulk side, you compute the index with the dBi action and fluctuations around.
Yes,
right.
yes.
This includes Besumino terms that typically depends on the gauge you use to write to the Ramon fields.
Mm-hmm.
And these are, so the difference with different gauges are different boundary terms. Do they play any role in the computation, or how do you fix that gauge choice?
I don't have a separate fixing procedure for the Ramon potential. I just chose a C4, which whose exterior derivative gives you the F5, which satisfies the 10-dimensional supergravity equations.
Right. But I mean, if you choose a different gauge for the C4, would you expect any change in the computation, or?
So I can't say for sure.
Okay.
I think I need to look into it. Thank you.
Okay, I have a very naive question. So where do these Schur polynomial operators that we heard about yesterday fit into your picture?
Sorry, can you repeat your question?
Yeah, yesterday we heard about Schur polynomial operators, which represent D-branes and which are orthogonal at finite n.
Mm-hmm.
So where do I see them in your analysis?
So the Schur polynomials are already included in the trace spectrum, right? So this finite n spectrum, 1 over an index from 1 to n, 1 minus q to the index. These Schur polynomials are already counted by this.
Okay.
So remember that you know, these shared polynomials have expressions in terms of traces. They're not orthogonal from the traces.
No, but they are mutually orthogonal, of course.
They're mutually orthogonal, but this is already included in the gauge theory counting of states in the half BPS sector. Okay. I'm actually, the kinds of trace relations that I'm describing actually are ones that you would get by considering too many rows in the short polynomial. So short polynomials are a way to produce these trace relations. Maybe that's the relation, but
okay.
So here, so people also looked at like a DC Branes probe in the 1/16 BPS black holes.
Yeah.
Do you think there will be also some minus signs if you start computing one loop fluctuation around it?
So this really depends on the cycle that they wrap. So if they considered a giant-like Euclidean D-brane wrapping an S3 and S5, then I would suspect that there are these unstable modes which give you an overall minus sign from the one loop term.
All right. Let's thank Hoon and prepare for